Hey everyone. I realized that finals are coming up soon, and I had a specific request from one of my students to make a video clearing up some chemistry concept that she was struggling with. So we have a few concepts that I'm going to be going over in this video. So the first topic is going to be naming compounds. And remember that in chemistry, a compound is something made up of multiple atoms. So it could be a molecule, or it could be made up of multiple different compounds. So it could be like a molecule like this, or it could be made up of multiple different molecules. And in chemistry, we have really specific rules when it comes to naming these things. It depends on what kind of molecule it is, and each type has its own particular naming rules. So let's talk about the different types real quick that I'm going to be going over in this video. So we have covalent compounds. We have ionic, and I'm also going to be going over acids. So a covalent compound occurs whenever we don't have a transfer of electrons in an ionic sense. So it would be a little easier if I explain ionic first, and then we can compare and contrast ionic and covalent. So an example of an ionic compound would be magnesium nitrite. This one's ionic because we have an ionic bond. We have a cation and we have an anion. And these charges are going to tell us how exactly to name this particular compound. So we'll get into that in a little bit. That's an example of an ionic. So there's an ionic bond between the cation and the anion. So a covalent compound is made up of covalent bonds. So electrons are going to be shared evenly instead of them being exchanged and pulled towards one particular atom like they are in an ionic compound. So an example of a covalent compound would be HCl. And this is also an acid, so maybe that's not the best example. So an example of an ionic compound would be, I think the most common one would be carbon dioxide, CO2. And let's talk about how we're going to name this compound. So the naming rule we use for covalent compounds is we name the atom, or we name the element that appears to the left, farthest to the left, or farthest down on the periodic table. So in this case, carbon appears to the left of oxygen, so we name that one first. And then we always use the numbers that indicate the number of atoms to tell us what the prefix should be on every atom. So for example, 2 means bi. A bicycle has 2 wheels. Biannually means every 2 years. So we're going to be using a lot of Latin to help us write these prefixes and name the compound. So C is carbon. There's only one of them, so we don't need a prefix there. Up next, we have oxygen. We have 2 of those, and typically, I know I just said bi means 2, but di also means 2. So in this case, we're going to be using di instead of bi. So this is carbon di, and normally it would be carbon dioxygen, but whenever we're dealing with something like this, the second element always has its ending replaced with "ide." So oxygen turns into oxide. So this is carbon dioxide. And then, like I said before, the last one we had is an acid. And the kind of the dead giveaway that we have an acid is that it starts with hydrogen. This is always going to be the first component that makes up an acid. And we'll get into the acid rules a little bit later. So we've named carbon dioxide. That's a covalent compound. Let's try a few more. Let's try something a little different. So this is a polyatomic ion. It has a really specific name, but for now, we're going to go by our binary covalent compound rules. So sulfur appears to the left or below of oxygen, so that gets named first. So sulfur, and then just like last time, we have oxygen. The last part of oxygen is going to get replaced with ide, and then this means we're going to have 3 of those. So we're going to call this trioxide. So this is sulfur trioxide. So that's how we name this compound. And maybe we can do one more. Br5, F10. So Br is the symbol for bromine, F is the symbol for fluorine. So this 5 means we have 5 atoms of bromine, and then the 10 means we have 10 atoms of fluorine. So I think of pentagon when I see 5. A pentagon has 5 sides. So the prefix for this is going to be penta. And then a decagon has 10 sides. A decade has 10 years. So DEC is the prefix we use for 10. So this is going to be pentabromine. So we write the prefix and the entire element for our first element. So penta, that doesn't look good. Pentabromine. And then this is dec. So this is going to be decafluoride. Fluorine becomes fluoride. So that's naming covalent compounds. Not too difficult. Just take some practice. Ionic compounds are a little more involved, a little trickier. They have more demanding rules we have to adhere to. So let's give a few of those a try. So let's say we have, what would be a good one? Let's start with something neutral first. Something that's electrically neutral. Hg, HCO3, and we have 2 of those. So let's talk about how to name an ionic compound. So it's pretty similar, but with ionic compounds, remember we have a transfer of charges, and that's based on the octet rule and the optimal number of valence electrons, which is 8. So atoms are going to bond together with their goal of having 8 electrons in their valence shell. And that's where we get our common ion charges that we know. So Hg is mercury, and then HCO3 is bicarbonate. Bicarbonate has a -1 charge. We have 2 of those, so that means the total charge on the anion bicarbonate is going to be a -2. And then mercury, the charge on this one is going to be a +2. So this is already neutral. We have a +2 and a -2. They cancel each other out, which means this thing is electrically neutral, which is exactly what we need to have. So if there's no specified charge right here in the top right-hand corner, that means it's electrically neutral. They add to 0. If we had a -1, that means they need to sum to -1. Same thing if we had a +3 or anything like that, but this one is just nothing there, so it's neutral. So let's talk about how we name this. So Hg is mercury. Just like with ionic or covalent compounds, we start with the first element, and then we have this polyatomic ion. This is carbonate. So this is just going to be, well, mercury is a transition metal. And whenever we have a transition metal, we always indicate the charge with a Roman numeral in parentheses like this. So mercury has a +2 charge. So this would be a +2. And then our anion is carbonate. So this is mercury 2 carbonate. Let's try a different one. Let's try NaOH. So Na is sodium, and then OH is another polyatomic ion. This is called hydroxide. So let's list the charges. So sodium has a +1 charge. Hydroxide has a -1. They're already neutral. The +1 and the -1 cancel each other out. So that means altogether, we just write it like this. So sodium stays the same. And then the polyatomic ion, we don't need to modify any of the charges. We don't need to modify any of the qualities or quantities because it's already electrically neutral. So this is just sodium hydroxide. Let's try a more involved one. Let's say we have chromium 4 carbonate. So let's go backwards. We have a name. Let's see if we can create the formula from this name. So let's talk about the middle part first. This Roman numeral 4 in parentheses. That means the chromium cation has a +4 charge. Chromium is a transition metal, which means it has a variable charge. It has a few different discrete charges it can have, 4 being one of them. So this 4 in Roman numerals tells us that this 4, the chromium is going to have a charge of 4. So it lost 4 electrons, and it has a net charge of +4 as a result. And then the carbonate, that's another polyatomic ion. So chromium is Cr4, and then carbonate is CO3. That's carbonate. So now we have to ask ourselves, how many carbonates do we need to make this neutral? So a carbonate on its own has a charge of -2. So we have a +4 cation and a -2 anion. So the question is, how many carbonates do we need to make this neutral? How many -2s are needed to make it a -4? The answer is 2. We need 2 of those. So the formula for chromium 4 carbonate based on the +4 charge is CrCO3 2. So it's 1 chromium atom for every 2 carbonate molecules. That's the ratio we need between the 2 to keep this electrically neutral. Okay, not too bad. But let's try a few more. Let's say we have this Fe, and then C2H3, O2, 2. So back to naming it. So we have a formula, and we want to figure out the name of this molecule, of this compound. So just like last time, let's identify the cation and the anion and their charges. So Fe is iron. Iron is a transition metal. We don't know the charge just yet, but we can figure it out. So this polyatomic ion in parentheses, this is acetate. And we have 2 of those. And now let's figure out the charge needed for iron to make this neutral. So acetate has a -2 charge, and we have 2 of those. So that means the net charge on the anion is going to be -4. And then oops, I made a mistake there. So acetate has a charge of -1. 2 of those collectively would have a charge of -2. There we go, that makes sense. So that means for this to be neutral, the iron has to have a charge of +2. We want them to sum to 0. So let's write the name. So we know Fe is iron. We know that the iron is going to have a charge of +2 to make it neutral. And then we have acetate. So this formula corresponds to iron 2 acetate. All right, so let's talk about naming acids. So acids have their own really specific rules for naming. So acids always start with H. H is they're going to be the cation in an ionic compound because acids are always going to be ionic, a cation and an anion, and hydrogen is always going to be the cation in an acid. So there are 2 types of acids that we're going to be talking about in this video. So they are binary acids, and oxyacids. So binary acids are the simpler of the 2. So an example of a binary acid would just be hydrogen and one other element. An example of an oxyacid would be hydrogen and then something involving oxygen, most commonly a polyatomic ion. So each of these different kinds have their own specific rules for naming. So with a binary acid, we always start with hydro. Doesn't matter what elements we have, the name always starts with hydro. And then we have the element, the anion is going to have sorry, I can't talk right now. the anion is going to have its last part removed, the last part of the name, and then that is going to be replaced with ic and then acid. So this is chlorine. Cl is chlorine. Chlorine is going to turn into chloric. Chloric. So we have hydrochloric, and then we put acid at the end. So HCl is hydrochloric acid. So oxyacids have different rules, and it depends on the name of the polyatomic ion. So you want to have the polyatomic ion's name either committed to memory or have some kind of system you can use to tell what this name is, because it's going to come into play when you want to name the acid. So if the polyatomic ion ends in 8, the acid is going to involve an IC prefix. If the polyatomic ion ends in ite, it's going to be using an OUS. I said prefix, but I meant suffix. An ic suffix and then an OUS suffix. So let's see what we have here. So we have PO4 and PO4 is phosphate. So that means we're going to be using the ic prefix when we're naming this acid. So we don't need hydro when we're naming an oxyacid. We just start with the base of our anion, of our polyatomic ion. So this is phosphate. So we're going to start with phos, and then it's 8, so it's going to involve ic. So instead of phosphate, it's going to be phosphoric acid. Not too bad. Let's try another one. Let's say we have H and S, hydrogen bonding with sulfur. So just like normal compounds, an acid has to be neutral unless it's stated otherwise. So this does not have a net charge. So this one has to be electrically neutral as well. So the charge on a hydrogen atom is +1. The charge on a sulfur atom is -2. So we need 2 hydrogens to make this neutral. So we want this to be a +2. This is already a -2. So hydrogen is not a metal. So we can't change the charge like we did with transition metals. Instead, we change the quantity. So we're going to make this 2 hydrogens in order to make this neutral. So this 2 does not affect the name of the acid. It only affects the compound name when we're dealing with covalent compounds, not acids. So this is binary. So we're going to start with hydro. And then we have S. So just like with hydrochloric acid, we're going to start with sulfur. So sulfur is going to end in ic. So this is going to be sulfuric. And then acid. So H2S is hydrosulfuric acid. So let's try another oxyacid or two. So let's say we have hydrogen bonding with phosphite. So this is also not neutral because phosphite has a -3 charge, and we need 3 of these hydrogens to make it neutral. So we're going to make this H3 PO3. So now this is neutral. 3 hydrogens have a net charge of +3, and then the phosphite has a net charge of -3. So together they make up a net charge of 0, so it's neutral. So we're going to name this the same way we named phosphoric acid. So we still have phosphate as the first element in this polyatomic ion. So this is phosphite. We're going to remove the suffix and replace it with OUS because we have this naming convention. Phosphite turns into phosphorus. So this is going to be a phosphorus acid. We only need hydro when we're dealing with a binary acid. And I hope I'm spelling this right. So that's the difference between phosphoric acid and phosphorus acid. Let's try maybe a couple more. Let's try HCl So let's look at the anion. This is perchlorate, and 8 goes to ic. So that means perchlorate is going to turn into perchloric. Perchloric acid. And then let's do, I think, one more. I'm going to just show you one that doesn't exactly follow the naming convention, but it's good to know what it is anyway. So let's say we have, so hydrogen is at the beginning and at the end. So that's due to the bond geometry and the way both hydrogens bond with our anion. So in some cases, we put hydrogens together. In some cases, we leave it like this. So acetate is another one where we sometimes write it as hang on a second. So sometimes acetate can be written like this. So that's not the focus of this video. This is not a topic that's going to be on my students' midterm, so we're not going to dive into that today. But nonetheless, let's still use that as an example. So let's say we have this is formic acid. So we don't really have a trick for naming this. This is one of the ones you have to remember. It's kind of like polyatomic ions. So some of them have tricks for remembering. So like, for example, the oxidation states in phosphate versus phosphite, that is a trick you can use to help you identify which is which. So 8 has a higher oxidation than ite. And then you have polyatomic ions like permanganate, for example. We don't really have a trick for that one, and this is similar. So this is one of the ones you just want to commit to memory because it's going to be one of those ones where there's not a specific way to remember it. Okay, so we've named compounds and we've named acids. So let's move on to our next topic of this video. So our next topic is the idea of an empirical formula for a compound or a molecule. So a molecule, we know, can have different combinations of different atoms. So C2O10 would be an example. So this is a molecular formula. The difference between a molecular and an empirical formula is that the empirical formula would be the simplest whole number ratio between the two or more numbers of atoms. So 2 to 10 can be simplified to 1 to 5. So this top one is the molecular formula. This bottom one is the empirical formula. So we had a particular problem that we wanted to go over in this video. So let's say we want to find the percent composition of oxygen in aluminum hydroxide. So what we need to do is figure out the atomic mass of each of these things. So the atomic mass of 3 oxygens is going to be 16 times 3, which is 48. And then we need the atomic mass of the molecule, which is 78. So we're going to multiply that ratio by 100 to get us a percent. And then we get 61.54%. So this is the percentage of the composition that oxygen makes up. And now let's talk about how to make an empirical formula. So let's say we have 25 grams of sulfur and 25 grams of oxygen. And we want to create an empirical formula based on the molecule that they form. So we need the molar mass of each of these things and we need to convert them into moles. So for sulfur, we're going to take the number of grams, we're going to divide by the molar mass. So 1 mole we know is equivalent to 32 approximately grams. So if we do the math, we end up with 0.78 moles of sulfur. And then if we do the same thing with oxygen, we know oxygen has a molar mass of 16. So we're going to multiply our 25 grams of oxygen by 1 mole over 16 grams in every mole of oxygen. So that result is going to be 1.56 moles of oxygen. And then from there, to get the empirical formula, we need to make a ratio of one element to another, their molar, the number of moles we have for each. So we have the number of moles of sulfur on top, the number of moles of oxygen on the bottom. And for this particular one, we are going to approximate because oftentimes we care about getting something really simple and we have to get approximate numbers of moles in order to make the math work nicely. So we have 0.75 if we approximate that, if we round, and then we're going to round this one to 1.5. So this is going to work out to be 2/5 as a simple ratio. So then we're going to write it as 2n N2O5. So this would be the empirical formula of nitrogen reacting with oxygen if we have 25 grams of each. So now let's do one more example. So let's do the opposite. Let's determine the molecular formula from the empirical. So let's say we're trying to determine the molecular formula for BH3. And I meant to make that a little subscript at the end. So BH3, we want the molecular formula for this. So we have two different values we're going to be using, two different values we need to consider here. So we have a molar mass, which is 27.7, and we need to figure out the empirical formula mass. So the molar mass is going to be different from the empirical formula mass, and the molar mass comes from the sum of all of the masses in the molecular formula. So the molar mass is going to be bigger typically than the empirical formula mass because, for example, this could be a possible molecular formula for the same compound because 2 to 6 form that 1 to 3 ratio. So this would be an example of a molecular, and then this would be an example of an empirical for the same compound type. So it just depends on how many grams and how many moles are present in the sample. So obviously, the more moles you have, the bigger your subscripts are going to be, the more atoms you have in the molecular versus the empirical. So we have our molar mass, and we need to figure out the empirical formula mass. And we get that just by adding the molar mass of 1 boron atom and 3 hydrogen atoms. So when we do that, we get approximately, empirical formula mass is approximately 13.811. So now that we have that information, we want to divide the molar mass by the empirical formula mass. And then we get approximately 2 for this. So this is the ratio we need to multiply the number of atoms in the empirical formula by to get the molecular. So if this is our empirical formula, BH3, we're going to multiply the number of atoms in each element by 2. So 1 is going to turn into 2. And then H is going to turn into 6. So this right here is the molecular formula. And then BH3 is the empirical. So that's the main difference between those. And we don't really have time to do any more, but I hope that was helpful. And if you need any more help with chemistry, feel free to contact me and I'm happy to make some more videos. All right, see you guys later. Adios.